Welcome to Mission Control. I am your flight director, and today we are launching an exhaustive, hyper-focused simulation for one of the most critical payloads in the Cambridge syllabus, AS and A-Level Mathematics 9709, Probability and Statistics 2. Our target coordinates? Mastering linear combinations of random variables. This is not a basic training drill. We treat Cambridge syllabi like critical flight launch protocols. There is absolutely zero margin for error here. To my right at the primary telemetry station is pilot Alex, our lead propulsion engineer, and to my left is pilot Sam, our elite navigation specialist. Together, we are going to decode the exact strategies required to maximize your exam score and push your grade propulsion meter all the way to maximum yield. Let us initiate the launch sequence. On our central viewing monitor, we are projecting the target orbit profile. Listen closely to this direct intercept from a Cambridge senior examiner.
The difference between a B and an A-star in mathematics often comes down to how well you understand linear combinations.
Director, if I am analyzing the telemetry on past papers correctly, a low-altitude descriptive trajectory, basically just memorizing the formulas, will only ever get a candidate into the B-grade atmosphere.
That is exactly right, Sam. To achieve a high-propulsion A-star launch pathway, you must possess a flawless mechanical understanding of independent random variables. B-grade candidates treat these equations like simple input-output machines, but A-star candidates act like systems engineers. They know precisely when to scale an expected value, and they know the absolutely critical difference between a multiple of a single variable and the sum of multiple independent variables. If you miss that distinction, your entire flight path burns up on re-entry.
To ensure we clear every atmospheric limit and hit every assessment objective, here is our structured roadmap. Phase 1. Core principles. Phase 2, the procedural framework. Phase 3, critical examiner warnings. And Phase 4, the exam strategy checklist. Flight Director initiating Phase 1, core statistical principles, the foundations of 9709. Let us calibrate the launch track. Flight Director, I am overloading the central console with raw fuel logs right now. I have got the expectation and variance formulas locked in. For the expected value of a linear combination, E of aX plus b, the math scales perfectly linearly. It simply translates to A multiplied by E of x plus the constant b. It is a highly efficient transfer of energy.
Hang on a second, Alex. You are moving too fast. Look at your variance logs. Variance is a measure of statistical spread, like the turbulence acting on our hull. Adding a constant b just shifts the entire distribution along the axis. It does not change the actual spread, so the plus b drops off entirely.
Affirmative, Sam. And the multiplier A?
The multiplier a gets squared, Alex. The variance of ax plus b becomes a squared times the variance of x. Why? Because variance is intrinsically based on squared deviations from the mean. If you scale a value by a, its spread scales by a, which means the variance scales by the square of a. Now, crew, look at the combination of x and y. To successfully execute the formulas for E of ax plus by, and specifically the variance of ax plus by, there is one non-negotiable structural boundary coordinate.
Independence.
Exactly. The variables must be strictly unconditionally independent. If x and y are not independent, covariance introduces parasitic drag, and this standard variance formula completely disintegrates mid-flight.
Flight Director, Cambridge prioritizes analytical depth over superficial breadth. The examiners specifically target 3 distinct cognitive domains to stress test your reasoning. At the baseline launch pad, we have knowledge and understanding. That is simply recalling your fuel logs, remembering to square the multiplier for variance. But to break orbit, we have to scale up to application and analysis.
Right. An evaluative launch pathway means looking at a complex, chaotic word problem and recognizing instantly that you are dealing with independent variables. You have to extract the exact mean and variance and then analyze how this new combination shifts the normal distribution probability.
Precisely, Sam. And let me be clear to everyone running this simulation. Misinterpreting a command word in this phase triggers an immediate system failure alert on your examiner's dashboard. You must match the exact cognitive domain requested. Flight Director. Moving to Phase 2, the procedural framework, systematic processing. Here is the strict, standardized, 5-step procedural framework you must lock into your navigation system for every single question. Deconstruct, extract, select, execute, and present. Alex, Sam, let us run a peer telemetry coordination debate. I am loading a common exam scenario onto your screens. A cargo elevator is loading 3 random crates of type X.
Tracking. Okay, I am extracting the relevant data. To save time and fuel on the exam clock, I am selecting my analytical framework. W equals 3x, maximum efficiency.
No, Alex. Immediate structural boundary violation. If you run W equals 3x, you're assuming the payload is one single crate of type X, and you are just multiplying its exact physical weight by 3. That is a completely different physical scenario.
But the problem says 3 crates, 3 times x. It is the same total weight.
No, it is not. The crates are individual, independent items. The correct framework has to be x1 plus x2 plus x3.
Sam is exactly right. Alex, look at your variance readouts if you use your framework. If you use 3x, your variance will calculate as 3 squared, which is 9, times the variance of x. That simulates taking one crate, multiplying its weight by 3, and massively amplifying its natural variance. But for 3 independent, separate crates, the actual variance is the variance of x1 plus the variance of x2 plus the variance of x3. That is just 3 times the variance of a single crate. 9 times versus 3 times. That is a massive trajectory error. Selecting the analytical framework requires absolute, uncompromising precision.
Flight Director, launch trajectory hold. Freeze all telemetry consoles. I am taking override control. Before we deploy this top-band paragraph structure and mathematical layout to clear orbit, we need to optimize your educational flight deck. Take a second right now to subscribe to Ace the Exams at the handle @AceTheExams and enable all notifications so you never miss our weekly flight-tested exam hacks. Whether you are launching at IGCSE, O-levels, or AS and A-levels, we give you the exact coordinates to secure the maximum grade. All right, simulation unpaused. Crew, we just experienced an unexpected structural data loss mid-calculation. Your evidence links are dropping. How do we stabilize? We stabilize using strict presentation conventions, proper headings, correct terminology, clear annotations. Exactly. Professional skill and application requires adhering to these conventions without fail. You must explicitly define our variables on the page so the examiner can read your telemetry. Explicitly state your expected value equations, and physically write out that because the items are independent, your variance adds up accordingly. If your notation is a mess, the examiner cannot trace your logic string, and your mission is terminated. Flight Director initiating Phase 3, Critical Examiner Warnings, the Pitfalls. Straight from the Cambridge Principal Examiner reports, our radar has identified exactly 3 recurring structural flaws. 3 mistakes that cause well-prepared students to needlessly hemorrhage marks during the final descent. I am handing manual control over to you, the viewer, for our interactive radar check arena. Challenge 1, the visual radar sweep. I am putting a 60-second visual countdown timer on your internal clock. Look at these top 3 student mistakes. 1, answers are far too vague. 2, forgetting format. 3, answers are not specific to context. I want you to extract the single highest yielding core trend here. What is the fundamental logic malfunction connecting mistake 1 and mistake 3?
Director, I am seeing it on the radar. It is a failure to link mathematical theory to the physical reality of the question.
Spot on, Sam. For example, if a question asks you to state one assumption required to calculate the variance of a total weight, an average student writes, the variables must be independent. That triggers a total system failure. It is vague, it lacks contextual specificity, and it is just raw textbook data dumping. Welcome to Challenge 2, Identify the Logic Malfunction. On your monitor, we are comparing a flawed medium-tier response with a perfectly engineered A-star response. Look at the left side. X and Y are independent. This response floats aimlessly in a vacuum. It ignores the constraints of the environment.
So how do we restructure the paragraph layout to perfectly match the examiner's compliance criteria?
We lock it to the coordinates of the question. We rewrite the response out loud, line by line. We say, it is assumed that the weight of the crates of type X are completely independent from the weights of the crates of type Y, and independent of each other.
Perfect execution, crew. By explicitly integrating the physical crates and their specific weights into your logic string, you establish a direct analytical link that secures the elite marking bands. Contextual specificity is your strongest armor.
Red alert, flight crew. Examiner alert on the main screen. We have a catastrophic hardware malfunction. Alex just punched the wrong standardized value into the calculator at the very end of a massive normal distribution probability calculation. The final numerical answer is totally corrupt. Are we losing the mission?
No, Director. We deploy the method mark strategy. Even if the final thruster calculation is wrong, strictly following the method mark protocol by making our analytical working visible on the page completely saves the grade.
That is the mark of a master engineer. If you clearly show your expected value calculation, detail your variance calculation, and manually write out the standardization formula, z equals w minus the mean divided by the standard deviation, you secure the method marks. The Cambridge marking scheme awards heavy marks for your process telemetry. Never, ever execute complex linear combinations purely in your head. Write out every single step on the page to build an unshakable safety net.
Flight Director, initiating our final phase. Phase 4. Exam Strategy Checklist, Final Review. Flight Director, we are approaching the summit of our flight path. Alex and Sam, I am watching your propulsion meters peak at a maximum A-star reading. Let us distill this entire simulation into 3 universal, non-negotiable rules for your post-launch system review. Rule 1. The 3-step question scan. This is your decoding phase. You must scan the command words to determine if you are calculating a scaled multiple of one observation, like 3 times x, or the sum of independent observations, like x1 plus x2 plus x3. Rule 2. The fuel budget allocation. Time is your fuel. Do not rush the variance calculation. Ensure you are squaring your coefficients correctly, and remember the golden rule. Variance is always added, never subtracted. Even if the linear combination is x minus y, the variance is var x plus var y. And Rule 3, the system review checklist. Verify every assumption you write is bolted directly to the precise physical scenario provided in the paper. Flight Director, as we complete our flight path and prepare for splashdown, I leave you with this final critical radar check. Ask yourself this question every single time you sit down to practice 9709 linear combinations. Are you showing enough clear, annotated working to secure your method marks and guarantee your A-star? When the clock is ticking down in the exam room and the pressure is critical, your standard of presentation is your absolute best defense. This concludes our mission control simulation. Do not forget to subscribe to AC Exams at the handle @ACExams. Click the notification bell to receive our weekly masterclass coordinates, and drop a comment below sharing exactly which Cambridge subject and level you are preparing to conquer next. Stay sharp, stay focused, and I will see you in the next explainer.